If we look up here, all the boards have the same correct answer. We know that the heat of water is the specific heat times the mass times delta T. So we have to look up the specific heat. We know the mass. We know the temperature change. We get 5,200 joules. The heat for the ball bearing is the heat capacity times the temperature change. The 190 comes about from the final temperature, 30, minus the initial is negative 190. Now you notice I kind of slipped a sign here because I was looking at the absolute value. So it should be negative. And then we put that negative sign in here. And we get 2 negatives, so we end up with a positive heat capacity, 27 joules per degree C. So the question that came up was, how do you know which temperature to use for final? Because the ball bearing and the water have the same final temperature. Okay, was there another question? Because it's cooling down. It's cooling down. So it really wasn't that important in any of the previous examples to worry about that negative sign because you could use the absolute value. But when we look at the next problem, you'll see why it's algebraically important to solve for that negative sign. Yes, Rob? Not the high temperature, the final temperature. It's not because it's higher, it's because it's final, and it happens to be higher. Because the water starts out at 25, then when you dump the hot metal in there, the water warms up. And as the water is reaching 30 degrees, the ball bearing is cooling down to 30 degrees. It's at thermal equilibrium. They end up being the same temperature because they're completely in contact with each other. No, we're not saying, oh, it's in this range. It was at 25. We checked the temperature. At the end, it was 30. Okay. So now, when we look at this problem, this one is quite a bit fancier. We have a 15-gram piece of gold was heated to 150 degrees C. So the gold is now 150 degrees Celsius. We drop it into 200 grams of water at 23 degrees. What's the final temperature of the water? This one is different because we don't know the final temperature. So when we start thinking about this, you say, well, what do I know? I know that the heat lost by the gold is equal to minus the heat gained by the water. So now we say, well, what information do I have to go look up? I'm going to grab my specific heat chart and I'm going to look up the specific heat of water and I'm going to look up the specific heat of gold because we need that information. And we know that heat is equal to specific heat times mass times delta T. We're choosing to use specific heat in this problem because we have masses of each of the species. Since we have mass, we need specific heat. If there was no mass, we would need heat capacity. So the heat of the gold is equal to the specific heat of gold, 0.129 joules per gram degree C, times the mass of gold, 15 grams, times the temperature change. What is the temperature change for the gold? We don't know, but we know that it's always final minus initial. So we don't know the final, so we'll call it T sub F, minus the initial temperature of the gold, 150. So that's equal to minus the heat of the water. The specific heat of water, 4.18 joules per gram degree C, times the mass of water, 200 grams, times the temperature change for the water. What's the temperature change for the water? We don't know. So you can't have two variables, but what we do know is that the final temperature of the water and the final temperature of the gold are the same. So T final minus T initial 23.0 degrees C. So now, because I have the same final temperature on both sides of the equation, I have an algebraic equation with a variable. So this problem is more challenging because you had to think about this, think it through, and set up an equation with a variable. Now we just chug through the algebra and solve this equation. So when we look at this, the first thing I'm going to do is just multiply these two numbers together. So I get 1.94 joules per degree C times T sub F minus 150 degrees C. That's equal to a negative 836 joules per degree C times T sub F minus 23.0 degrees C. So now I get T sub F is in degrees C, so I get 1.94 T sub F with units of joules minus multiplying 1.94 by negative 150, I get a negative 291 joules. I've got units of joules here times, oh, I already wrote it in there, times T sub F is equal to negative 836 T sub F joules. Negative times a negative becomes positive plus 19,200 joules. So now I have two T sub F variable terms and two numbers, so I'm going to rearrange to get everything on the same side. So I'm going to start by adding 836 T sub F joules to this side. So 1.94 times T sub F with units of joules plus 836 times T sub F in units of joules is equal to 19,200 joules plus 291 joules. I'm adding 291 to both sides. So when I add these together, I get 838 T sub F is equal, in joules, is equal to 19,500 joules. So T sub F is equal to 19,500. How did I drop something? I'm working on that. It was the unit that was confusing me. Somehow I dropped my unit of degrees C because we end up with T sub F in degrees C. Oh, I canceled it out earlier saying it was joules per degree C, but that's okay. It comes out. 19,500 divided by 838 is equal to T sub F 23.3 degrees Celsius. So when you look at this, you say, does this seem like a reasonable answer? And the answer is yes. I got a little sloppy tracking my units there, but it comes out in degrees Celsius. So you think about it, the water started at 23 and it only went up 0.3 of a degree. But that's okay because when you look on the next page at the specific heats, what do you notice? What do you notice about the specific heat of water? It's very high considered that you're comparing it to everything else on there. So, because this is high, what that means is it takes a lot of energy to heat water up compared to how much energy it takes to heat those other things. So this really opens some doors for us because we can use this idea in a calorimeter. We can take a device in the laboratory and put water in there, put our chemistry in a little container, and let all the energy from the container go into the water, and then it heats up the water and we can measure the temperature change and figure out how much energy we had. So that opens up the science of calorimetry to us. And there's a couple of different kinds of calorimeter problems. Some of the calorimetry problems use a bomb calorimeter where you're heating up water, and some of the calorimetry problems just use mixing solutions.